So now, operational amplifiers can be used to make all kinds of circuit. We're going to look at a very simple one here as a non-inverting comparator. So first off, you have to power the integrated circuit, pin 8 to positive supply, pin 4 to the negative supply. If you're using an LM358, we're using 1 out of 2 op amps right there. You set a reference voltage to the minus input right there, the inverting input. And we're going to set half of the supply voltage. Pretty simple right there. We have an adjustable voltage at the plus input, the non-inverting input, just using a trim pot to make some things simple for a demonstration circuit. So we got 2.5 volts for our reference voltage. When this voltage is higher, closer to 5 volts, that will set the output high. When this voltage at the plus is lower than the minus voltage, it sets the output low. When the output is high, the red LED will light up, and when the output is low, the blue LED will light up. So now, another simple circuit you can make with an op amp or a comparator is an inverting comparator. So we're going to use the LM358 op amp here, 1 out of 2 of them. Of course, you got to power it. So for this particular one, positive supply, pin 8, negative supply, pin 4. We are setting our reference voltage now to the non-inverting input right there. Remember, the output wants to be more like the non-inverting input. So we got half of 5 volts right there because we have an equal voltage divider right there. And so when this trim pot gets higher than half of the supply voltage right there, then the output will be low. It will be the opposite. You get the trim pot voltage lower than half of the supply voltage, then the output will be high. Again, it's going to be opposite because it's an inverting comparator. When the output is high, the red LED lights up, and when the output is low, the blue LED lights up. So now, a lot of circuits respond to light levels, and one way to wire that up is to use an op amp and a light-dependent resistor. We got this wired up as a non-inverting comparator, and we'll look at why. So to begin with, we set a reference voltage to make things easy, just half of the supply voltage right there to the inverting input. Notice though, the inverting input on the physical component is higher than the non-inverting. You got to pay close attention on the schematics where the plus and the minus is. But in any case, we got 2.5 volts there. When it gets bright enough, the non-inverting input right there gets a higher voltage, and the output will be high, as good as it can do. And when it gets dark enough, then the non-inverting input will get lower than 2.5 volts, what we set there. And thus the output will be low. The blue LED will light up. And remember, you got to power the integrated circuit, pin 8 to the positive supply, and pin 4 to the negative supply if you're using one of the LM358 op amps. Some mini circuits depend on light level for changing the output, which we can do with the op amp here. We have it as an inverting comparator though in this example circuit. So what that means is we set our reference voltage to the plus input, simply half of the supply voltage, keeping things simple, 2.5 volts. At the inverting input, and notice they're in different spots on the physical component. Always pay close attention to how the physical component's laid out. But at the inverting input, we have our voltage divider that depends on a light-dependent resistor right there on the high side right there. So we get it bright enough, it's going to get a high enough voltage somewhere. Some point it'll be above 2.5 volts. And then the output will be low. It'll be the opposite because this one has the lower voltage right there. If it gets dark enough, it's going to pull down that voltage at the inverting input. This one will have a higher voltage, and therefore the output will be high, and the red LED will light up. So now, another simple but very useful use of the op amp is as a voltage follower. So what you do is, in this case, we got a trim pot, and you got, or any other voltage divider, that you get a voltage, but you can't provide power. You just give that to the non-inverting input of, in this case, the op amp. You have the output here. The output wants to be more like the voltage at the non-inverting input than the inverting input. When you got a negative feedback connection there, a direct one, then the voltage is just going to jump right to whatever that voltage is. And when they're equal, it's going to stop. So hopefully that makes sense. The LM358, though, cannot output the full positive supply voltage. 9 in this case, it falls about a volt short or whatever. But in any case, it can provide enough current to light an LED. So you could adjust the LED brightness in that case. So that's really about all there is to it. So I'm going to end it there. So now I thought we would look at another simple fixed resistor voltage divider example. So you may be working with 12 volts right there. You want half of that voltage, 6 volts, as a signal. It's not for powering stuff. You could take a couple 1000 ohm resistors in this case and put them in series, and you'll get 6 volts right where they are divided. 6 volts across one, 6 volts across the other, but usually you use that voltage in relationship to ground right there. Now, we got 12 volts. There's 1000 ohms of resistance total right there. Remember, this output is not for providing current. And so with 2000 ohms, you're going to get about 0.006 amps of current flowing right there. So that's flowing through both of them. And so if you got 0.006 amps, 6 milliamps current, times 1000 ohms, the value of one of those resistors, you'll get about 6 volts across it. So that's just another example to help illustrate voltage dividers.